the upgradation or updation of the boundary condition. Okay. And yesterday we talked about, I think, two parts, probably 2 or 3 parts. We discussed about the background pre-processing in detail. We also talked about the observation quality control and the computation of the background error. That also we talked about yesterday. Right? Computation of the background error we completed. And today we shall discuss about the observation pre-processing and quality control. Okay, this one. So we have discussed about the errors in the observation in the beginning, right? Different types of observations, how they are coded in WMO's format, and then once they are received, they are decoded, quality control using different methods, including the CQC, the complex quality control, right? So we shall briefly summarize that now here today. The MM5 WRF 3D VAR has a module called 3D VAR OBSPROC, and this is a very important module because when you are trying to assimilate your own data, any new data which you are trying to assimilate, then you have to put this data or put your data into the format in which the WRF can understand or read it. And that is done through this 3D VAR OBSPROC, that is observation processor. Observation processor. OBSPROC is a short form of observation processes for pre-processing and quality control of observations. It packs the observations in suitable format for ingest into 3D VAR. The main functions of the observation pre-processors are as follows. Number one, read the decoded observations packed in WRF little r format. Okay, this is another important thing. We start using the laser pointer. Okay, little r format. Now this is very important part of the observation preprocessor, which all of you will have to learn. Because as I said, when you are trying to utilize your own observation in the model, then you must pack your observation into this format called little r format, okay, which WRF can read, right? The standard observations which are received, say from the sign-up or temp. You remember what is the temp? Which
So
format?
radios only. Radios
Correct,
only.
yeah, correct, yes. Temp is the reduce on format. So all these formats are anyway standard formats. Okay, but any new observation that you might collect, that is not in the standard format, so that you have to put into the WRF little r format. Okay. Then perform spatial and temporal checks to select only observations located within the target domain and within a specified time window. Now you understand the time window, right? The time window.
Yes, sir.
Right. So whatever observations that you have, that must be located within the domain of your model, right? And within the specified time window. Then you calculate heights for observations whose vertical coordinate is pressure. Okay, some observations are reported in pressure coordinate. So that has to be converted into the height coordinate. You have to assign the altitude in meters or geopotential meters where the observation is collected. Then merge duplicate observations, that means observations around the same location. I mean, well, same location means even if it is not exactly the same, but if it is nearby location. Like depending upon your model resolution. Suppose if your model resolution is 50 kilometer or 100 kilometer, okay, and you have observations located within 5 kilometer distance, then such a coarse grid of the model having 50 or 100 kilometer grid distance will have no meaning of observations which are very close to each other, not just 5 kilometer apart. So suppose one observation in the university campus and other observation, let us say, at a distance about 4 or 5 kilometers, like now, this Birla school in the Suraj, near Suraj, on the highway, Birla International School, right? You must have heard about that. Very close by. I mean, any observation which is nearby reported, that is almost treated like a duplicate observation. So such duplicate observations should be merged and choose a observation nearest to the analysis time for stations with observations at several times. Okay, these are the functions of the OBS proc, the 3D bar OBS proc functions are these. Also, it estimates and assigns error for each observation. Okay, for each observation, there are certain known errors. We had discussed that earlier. Known errors are like instrumental error, which is provided by the manufacturer of the instrument, right? So those observations are known. And any other error, suppose if there is a bias, suppose some temperature reported from a station has a bias of 1 degree or 2 degree every day. You know that the temperature reported by this station is 2 degree warmer or 2 degree colder than actual. So there is a bias, known error, right? Systematic error. So whatever known errors are there, those things are estimated and assigned, okay, to each observation. Then it performs a variety of quality control checks. That is, it checks if there is any negative wind speed, which is not possible, right? Vector wind speed, I mean, because U or V can be negative, but vector wind cannot be negative. So it checks any negative wind speed, spike in wind profile, and a sudden increase. Sudden increase can happen if there is a gust, right? There's a gustiness, sudden increase in the wind can happen. That is during thunderstorms or square lines, etc. But otherwise, normally, it doesn't occur, sudden gust. So any spike in the wind profile, it also tries to avoid the too much of errors in the analysis. Spike in temperature profile, super adiabatic lapse rate, height above or below the model lead. That means any observation which is mistakenly or erroneously assigned a height which is above the top of the model or below the bottom of the model. That can happen, right? So such observations are found out by the computer program, okay, and these things are filtered out. It checks the quality for that. Any super adiabatic lapse rate, if there is existing, that also is filtered out, or any spike in the temperature also filtered out, right? It's just trying to make the data smooth to avoid any problem in the analysis. Otherwise, it's likely that unnecessary for that observation point, it will show too much of error in the analysis when you are trying to minimize the error between observation and the first guess. Then assign proper quality control flag to each datum according to the result of the quality control checks. Okay, it assigns a flag to each data. I was telling you some time back probably that like suppose if there is a football team playing a match and then there is an umpire or a referee, and if some football player commits a foul or a mistake, then he will just take out a yellow flag from his pocket. He has got green flag, yellow flag, red flag, and show to the player that look, that is not allowed. That kind of kicking the ball or kicking the player himself is not allowed. And this is a warning to you. If you commit this kind of mistake again, then he will show a red flag to him, so that you are out from the game. Right? You have seen that in the football match, right? In soccer games. isn't it? So similarly, the data are assigned different kinds of flags, like a red flag or yellow flag, green flag. All the data which are good quality, they are put the green flag so that they are used for the assimilation. If some data is doubtful, then it is shown a yellow flags, let us say, so that people who are sitting to check manually, they will just check manually. If there's something minor problem, then it will be removed. The minor problem will be removed and used in the simulation. If some data is really a bad quality data and it will have it will be put into a red flag and just dumped into a separate zone so that it can be investigated later that what is wrong with the data. So different kinds of quality flag is assigned to the observations. Then it generates the runtime diagnostics about the rejection statistics. After doing all that, it generates how many data were rejected and how many data were accepted in the analysis system. That is important because we must know that why data is getting rejected. Sometimes some data gets continuously rejected because of its bad quality, and then if now we find a problem that there is a problem in that instrument, then that instrument has to be corrected. Right? Probably I have told you this story or not, I don't know. That sometimes the ECMWF model was consistently finding a problem in a station in somewhere in Africa, and they monitored that observation in that station continuously for about 1 month, and they found that this station is continuously reporting wrong observations, right? So they immediately informed that country that look, that observatory has a problem because it is continuously reporting a wrong data for last 1 month. And then the Met Service of that country, they looked into it and they found that there was really a problem in the instrumentation. So they immediately replaced the instrument. So like that, right? So it's important to have the rejection statistics, why the data is getting rejected. And you know that data is collected, every observation is collected with so much of pain and so much of money is invested, spent, sometimes lakhs and crores of rupees are spent. Suppose, when you are launching a satellite, then several hundred crores are used for launching a satellite. And if the satellite is not giving you a correct data, proper data, that means there is a problem, wastage of money, right? There is some problem in the sensor, something is wrong. So that has to be investigated. Like, you must have heard about the megatropics. Have you heard about the megatropics? Megatropics? Anybody? Have you heard about the megatropics satellite? Megatropics satellite. No? Nobody has heard of megatropics satellite. Well, megatropics is a Indo-French collaborated satellite. It was launched, I think, 10 years ago, maybe around 2010 or 11, probably it was launched as a Indo-French collaboration. And it was supposed to be something similar to TRMM. You know TRMM, right? Prim? Everybody is silent. Am I audible to all?
Yes, sir.
Okay. So TRMM you have heard, right? Trim satellite.
Yes, sir. TRMM we have heard.
Exactly. Similarly, the government of India, ISRO, wanted to have a similar satellite called, it named as Megatropics. Mega is the Indian word, right? Meg means cloud, sky. And tropics also is the English word, but in French they pronounce as TRIPQUE, something like that. Instead of TROPICS, tropics, that we write in English, it is written as TROPIQUE, like a French people write. Because they named as a joint collaborated project name, partly Indian name and partly French name, Megatropics. That satellite was launched after a long effort, many years of collaborative research and assembling of satellite, design of the sensors, etc., etc. But soon after it was launched, I think out of the 5 sensors, it was supposed to be a good satellite. almost doing the same function as the TRMM. And it has sensors for observing the cloud microphysics, just like the TRMM satellite has a PR called precipitation radar, right? Profiling the precipitation in the vertical from the space, and also profiling the cloud microphysics, cloud hygrometer profiles. Similarly, Megatropics had 4 or 5 sensors, one for the radiation measurement, one for the cloud measurement, one for the fluxes, and so on. Now, one for the rainfall. So, unfortunately, immediately after it was launched, I think one of the important sensors stopped functioning. It started giving malfunctioning, and all the data were all useless, erroneous data, right? So that can happen, and sometimes some data can become erroneous because of many reasons. Sometimes there is a drift in the orbit of the satellite, or whatever. So this rejection statistics is very important, and that is one of the very good role of the NWP centers, because every day it prepares the statistics of how many data is rejected and how many data is accepted in the model. If too much of data is rejected, then it's a serious matter. It's a matter of concern, right? Like NCMRWF also, if you look at the NCMRWF website, you'll find a file called data statistics for today. Every day it will prepare data statistics. How many data were received in total, all types of data, surface, upper air, satellite, etc. All types of data, whatever was received globally, it will have in the statistics. It will also make a plots of the data which were received, its locations, and etc. etc. Then it will also prepare a list of the data which were rejected, outrightly rejected by the model assimilation system. Okay, then it will prepare a list of all the data which were accepted by the model but was later on again rejected in the assimilation. It was not utilized for assimilation. So at 3 stages, the data is checked, like how many were received total, how many were rejected because of the quality control, and how many were rejected because of the imbalances or whatever reasons in the assimilation system. And that is monitored and investigated later on. Okay, so that is very important. Then it packs the observations in 3D var format. That is in ASCII. That is a good thing for the little r format, which I was telling you just now, little bit earlier. In the little r format of WRF model, all the data is in ASCII format, so you can visually see yourself. If it is in a binary, then you cannot see, you cannot know what it is. But if it is ASCII format, you know that whether the temperature is really having a sensible magnitude, whether it is 25 degrees centigrade or 250 degrees centigrade, right? That can happen. The temperature can mistakenly be reported as 250 degrees centigrade, which is just not possible, right? So in ASCII format, all the data is packed. So there was the role of the observation preprocessor of the 3D var, OBS-PROC. Okay. Then the next important part of the 3D var is the var analysis itself, assimilation system, where it does the minimization. I was talking to you yesterday that in the 3D var, basically, we try to minimize the so-called cost function. Do you remember that? Cost function. Yes or no? You remember?
Yes.
Yes. We talked yesterday that in 3D var, we try to minimize a cost function, which is the sum of the observational errors and the analysis errors. Okay, we try to just minimize that cost function. So this is now the part of the main analysis system var. The var problem can be summarized as the iterative solution of the equation 3.1 that we saw yesterday to find the analysis state x that minimizes the cost function gx. Okay, and you recall this equation that we saw yesterday. The cost function Jx is given by the sum of Jb, background field, and observation Jo, observation field, is equal to half of x minus xb transpose b inverse x minus xb. This is the background processing error. Okay, plus half of the y minus yo, which is the observation. Okay, transpose plus e, observational error, covariance matrix, And F, if you remember, that is the representative covariance matrix error. Okay, inverse of that, y minus yo. Okay, so the two terms in J, namely the JB and JO, are the contributions of the background and observations respectively toward the total cost function J. Details of the variational analysis may be referred from the paper of Barker et al. 2003 that also you saw yesterday. Okay, so that is the job of the variational analysis, to minimize the cost function or optimize the cost function. Okay. Although the variational analysis is frequently described as optimal, it is so subject to a number of assumptions. Okay. Firstly, given both the imperfect observations and background information as inputs to the simulation system, the quality of the output analysis depends crucially on the accuracy of the prescribed errors. Okay, because you know that there are errors in the observations. Your observations are not perfect. There are errors in the background field. That is your first case because the model is not perfect. Okay, so these are the inputs to the simulation system. So the quality of the output from this simulation system will obviously depend crucially on the accuracy of the prescribed errors. Okay. Secondly, although the variational method allows for the inclusion of the linearized dynamical physical processes, real errors in the NWP system may be highly nonlinear. That you also know that NWP system, the dynamics of the atmosphere, many physical processes are nonlinear. Okay, so inclusion of the nonlinear processes in the model also now causes the, the problems in the variational analysis. Okay, this limits the usefulness of variational data assimilation in highly nonlinear regimes, that is in convective scale or in tropics. Okay, because of these problems, the assimilation system or the 3D VAR finds problem, especially in the situation which is highly nonlinear, like during the convective scale systems like thunderstorms, or in the tropics where most of the time the atmosphere is convective, right, or convectively unstable. So that was the third part of the 3D VAR. Now the fourth and last part of the 3D VAR is that after you have obtained the analysis at your domain at the model grid points, then you have to update your boundary condition accordingly with the new observations in the domain, right? And that is the job of the fourth part. So in WRF, the lateral boundary conditions originally computed from the global model data, because initially we prescribed the boundary condition from the global model. So that has to be updated once your new analysis has been obtained in the inner grid points of the model from the new observations, and by combining the new observations and the first case. So your all inner grid points have become updated because of the new observations, and so accordingly you have to also update your boundary conditions which were originally prescribed from the global model data. Now, only boundary conditions from domain 1 needs updating in WRF to a nesting mode, as boundary conditions for the inner nests are automatically calculated in WRF. Suppose you have got a nested domain in the WRF, a domain within a domain, or two domains within a parent domain, right? So if you are having a multiple domain in the WRF model, then you don't have to update the boundary conditions in all the inner domains or inner nests, because that get automatically updated once you have updated the boundary condition in the outermost domain, that is domain number 1. Okay, so this is the role of the function of the updation of the boundary condition. So that was about the 3D VAR. All right. Now let's talk about the 4D VAR. I would like to finish the 4D VAR also today, if possible. Right. Now 3D VAR and the 4D VAR. Are you able to hear me? Am I audible to you?
Yes, sir.
Okay, good. So in 3D VAR, as the name suggests, you are having a static data, okay, collected at a particular observation time at particular location. And that data you're trying to merge with the first guess or background field and produce a new analysis field or updated first guess field. Okay. And as I already told that now, you always consider a time window, say let us say plus minus 3 hours, centered on the time of analysis. Okay. But once you are running the model for the next 6 hours, and because all these things always happen in a delayed mode. Because the moment you have given a time window of plus minus 3 hours, that means the 00 UTC analysis, you are anyway waiting up to 300 GMT, right? Because you are waiting for the observations to come for 300 GMT. And once the observations have come up to 30 GMT, then after that you start processing those observations obtained in the last 6 hours, entire global observations. Let us say you are doing the global model, that's what is done at NWF or ECMWF. So you start decoding the observations in the model, then you start quality controlling the model, observations, okay. All those things take time. So practically what happens that by the time you make a 4 cycle of assimilation, already it is about 9 or 10 GMT. No, because of so many reasons. That means you are already delayed by about 8-9 hours, practically. Or sometimes, if you are very efficient, at least 5-6 hours, it automatically gets delayed. But within that 5-6 hours time, also new observations have come up, right? Because observations keep coming on time. And once you are running the model, integrating the model for the future time step, then by the time new observations have come or your model integration has reached at T plus say 6 hours or T plus 3 hours, in the next 6 hours or 3 hours also you have got new observations. So why not we make use of those observations also to correct the model forecast, okay? Because we know that model will be deviating from the observations, from the reality. So as and when the observations keeps coming, you try to utilize that in the model, right? And that means you are making use of the time also. X, Y, Z, and T, right? So now your variational assimilation has become 4-dimensional, 4D, right? And of course, it is complex, and there are many advantages that people have noticed. Now, this table is showing different types of observations, like land the synoptic observations obtained from over the land, the ARIP, the aircraft reports, the buoy, surface observations from the ocean, temp, the radiation observations, pilot balloon observations, and the ship observations over the ocean, different types of observations. And people found that, with their experience, like the 3D water system, I told you that every day a statistics is made of how many observations were received at the NWP center and how many were rejected, how many were assimilated. So you have a list of observations which were actively used and which were rejected. You see that now, out of the total, say how many, 3,800 plus 2,200, almost 4,000 observations, about 3,800, almost, no, how much, kitna ho gaya? 4,000 plus 6,000, 6,000, right? 38 plus 22, almost like 6,000 observations. Nearly 4,000 were rejected, only 2,000 were used. See? Similarly, for ARIPS also, there are a lot of rejection, 3,000 rejection. And of course, here 5,000 is used. Now, in buoy, also a lot of rejection, 616 buoys were rejected and only 136 were accepted. Similarly, for the temp, reduction observations, and for the pilot balloon, for the ship, and so on. So people found that so many data is getting rejected and they're not utilized in real-time forecasting. In past, in climatology mode, of course, even the rejected data is analyzed and corrected and utilized for the reanalysis. But if you are not able to utilize those data in real time online, then you are losing a very valuable information for making your forecast, right? Because you know that NWP is a initial value problem, right? That means your initial condition is not perfect because so many data is getting rejected, right? So then people realize that no, there is something wrong and we have to utilize now, try to utilize this data also as much as possible, and the one which keeps coming while the model is running. So in 40 bar, they accommodated all the data and found that now more data were accepted. 7,000 sign-off is accepted, only 1,000 is rejected. Similarly, more airip aircraft reports are accepted, more buoy data is accepted, right? More temp data is accepted, more pilot balloon data is. Pilot balloon is still less, I think, 42 versus 49. And SIP, there's lots of SIP. So there are definitely a positive advantage, a lot of advantage of utilizing 4D bar compared to 3D bar, although it is expensive, of course. Computationally, 4D bar is expensive. So in 4D bar, time window is broken into smaller sub-windows, being typically 1 hour wide each, while the full window may be larger than 3D bar, than in 3D bar. As a result, more observations can be utilized in the 4D bar, right? So instead of saying plus minus 3 hours, you are also extending, you're stretching your time limit so that till your observations are, all the observations are received, till your model forecast or model is getting integrated, you're trying to accommodate them in the analysis. In variational data estimation, the analysis is done by minimizing a cost function that you already know. Right? Say, for example, in 3D bar, this is the equation that you have already seen. Right? This is 3D bar equation. And 4D bar equation also is very similar. Minimizing the cost function in the 4D bar equation assimilation is also very similar to 3D bar. Almost same term, half x0 minus xb transpose, right? B inverse xo minus xb plus half. All these things are similar, except that this is a digital new thing, mi, which is a function of xo, right? Yi. Similarly, here also mi xo, where h is the observation operator. Do you remember yesterday we were talking about the observation operator? You remember that? Observation
Yes.
operator.
Yes,
Yes,
sir.
right. So, so this is the only difference between 3D var and 4D var. You have got this term, and this term is used to accommodate the extra observations in the stretched time window while your model is getting integrated with respect to the state vector x. Here, y vector, y vector containing all observations, that is, indicate the observations. These are the observation vectors. H, the so-called observation operator, which maps from model space to the observation space. XB, the background field, okay, that you know already. The first case, capital B is the error covariance matrix of the background field. You remember we were talking about the background error covariance. How do we compute the background error field, right? Forecast of 24 minus 12 hours for 1 month time, right? And it can be seasonally different, monthly or seasonally, and it should also be different for different model configuration, right? We discussed about that in detail yesterday. Then R is the error covariance matrix of observations. Okay, this capital R. The matrices are of the order of n square number of NWP variables and n square number of observations, right? This is the size of the matrix, n square by n square. Approximately 1014 by 108, that is for the particular center. Typical for NWP run at BMI is some Dutch Meteorological Institute. So, but that depends on your domain size and the number of observations used by your model. Okay. MI, this MI I was referring to, is the NWP model operator, which turns the state vector XO into its forecast value at time I. Okay. I was telling you that now, as the model is running or as the model is getting integrated, now as long as the observations are available during its integration time, you try to accommodate those observations and correct the model as it is producing the new values. So that is done through this operator MI. Okay, it's called the model operator. Right. So this is the only difference between 3D VAR and 4D VAR. I mean, important difference. Right? In 4D VAR, observations are built into the time slots I. Okay, time slots because you are extending the time window. Typically, time slots are 1 hour by. This enables one to use observations from the same site obtained at different times, and it minimizes the offset in time between the time of observations and the valid time of the forecast. Hence, against which observations are compared. Okay. The drawback is that the 4D VAR requires far more computer time. Right? Normally, R is assumed to be diagonal. Okay, that matrix you remember. Meaning the errors of the observations are not correlated. Okay, assuming that observational errors are not correlated. Mind you, it is not the observations, but it is the observational errors, okay, which are not correlated. That is the assumption. However, B background covariance error matrix contain non-diagonal elements which are very important to the data analysis, as they determine how the corrections of the background state due to the observations are spread spatially in the region of surrounding the observations both vertically and horizontally. Because in the 3D VAR, you are taking care of three-dimensional observations horizontally as well as vertically. And also, you are taking into account the impact of one observation and many observations into the analysis at different grid points. As I mentioned yesterday, explaining to you that even observations at faraway locations, like even if your point of interest, let us say my point of interest is a grid point in Suraj, but I will be interested in observations not only in the locations nearby Suraj like Ajmer, Jaipur, but also faraway points, Delhi, up to Delhi maybe 300 kilometers away, right? Or if it is a city like Delhi, then Delhi itself has many AWS systems, almost like 20, 30 automatic weather systems are placed in Delhi at different locations. Especially, you remember the Commonwealth game? Commonwealth game in India.
Yes, sir.
Yes, sir.
When was it held?
2010. 2010.
Yes, exactly. So during the Commonwealth game 2010, all the stadiums, the sports stadium in Delhi, there were I think 10 stadiums. I mean, besides the main, which is the Jawaharlal Nehru Stadium, JN Stadium, there are many stadiums now for different games. Like some stadium is for indoor games, some stadiums are for outdoor games, some is for the football, some is for the cricket and blah blah blah, all that hockey and so many things. Then there is a swimming pool, Talkotoda Stadium is for the swimming pool, etc. etc. Right? So for all the stadiums, forecasts had to be given by IMD, right? And that to a repeat forecast, right? So at all the stadiums, IMD install a automatic weather station. Besides the main observatory, which is there at the Safdarjung Airport near the India Met Department office, was number one. And of course, at the Palam Airport, that is Indira Gandhi International Airport. They are the two main observatory of Delhi, right? One is the Safdarjung Observatory or Safdarjung Airport, other is the Palam Airport. The two main observatories. Besides those two main observatories, actually, the observations which is shared on the GTS, you know the GTS, right? The observations which are shared on the GTS are only from these two stations, Safdarjung and Palam. But rest of the observations are not shared in the GTS. And that's why, every country has many more observations than what is shared in the GTS. So about 20 to 30 AWS, like beside those stadiums, AWS is there also placed in Noida, in our office, and same RWF, there was a AWS and many more, in Noida area, if you have heard about the Noida, many more. Similarly, the same thing is also true in Calcutta, all the metro cities, Mumbai or Chennai. There is one or two main observatory, but there are many automatic weather stations around. Okay. So, besides take into account the observations of the main observatories like Savarjang and Palam of Delhi. All nearby observatories also are taken into account. Of course, and depends on the resolution of the model. And this is possible only when you are running a very high resolution model, 1 kilometer or 2 kilometer resolution. Then you can utilize all these observations of different stadiums. If your model resolution is itself is 2 cores, like 20 or 30 kilometer or 50 kilometer, then obviously there is no meaning of utilizing all these high resolution observations, right? So this is the role of the B. Further, the correct correlations, I have to finish quickly, lead to a spreading of observational information concerning one variable to other variables not directly related to the observation, right? So if the observations are correlated, because you are trying to minimize the cost function, minimizing over the whole area, not one by one. So the correlation between different observations also spreads or influences the analysis. For example, an observation of temperature will lead to the corrections not only of the temperature film of the background state, but also of the pressure, wind, etc. Because temperature influences the pressure. Temperature can also influence the wind. So not only the temperature is influencing the temperature of nearby location, but also it is influencing the pressure, the wind, etc. Because they are all physically related. So in practice, the minimum is found iteratively. This requires an expression for delta xj, okay, gradient of the cost function. In deriving that, it is assumed that h and mi, the observation operator, and the forecast model operator, can be described by a Taylor expansion to first order around xb, okay, background analysis field for relevant values of x, so that hx is equal to hxb plus hxb of delta x, where this h is the so-called tangent linear observation operator. This h in the bold is called the tangent linear observation operator. Again, this is another complex thing. Is not denoted by such a simple notation, but actually its formula is quite complex. And to calculate the tangent of any model is very complex and takes a lot of time, computationally expensive. And delta x is equal to x minus xb, okay, also called the adjoint of the model. To compute the adjoint of the model becomes difficult, because especially the physical part, physical processes, physical parameterizations are not so easy to calculate the adjoint of the model. So this is called the analysis increment x minus xb delta x. In 4D VAR, it is further assumed that within the data assimilation time slot, the model can be linearized for the time evolution of the increments such that mkxo minus mkxb, where this is the observation, this is the background field, is approximately equal to sum of the ml, where L is equal to 0 to K, all the observations time delta xj, delta x0, okay. The 4D VAR finds model trajectory that best fits observations over a time window, okay. But requires linear tangent and adjoint, which I just mentioned, adjoint or tangent, which is difficult to code computationally, computer-wise, programming-wise, not so easy to code. Compute the adjoint or tangent of the model. Or linearity of the error growth assumptions made, and we assume that within the time window the growth of the error is linear, which is also questionable. Can we assume that that is linear growth in the error? What if forecast model trajectory is unlike real atmosphere's trajectory? Model error, which is model error. These are the problems of the 4D VAR. And therefore, people started thinking further that now how to improve it further, how to correct these problems. And then they thought of using a so-called ensemble-based approach. Okay, ensemble data assimilation, they call it ensemble data assimilation, to get around these problems. Okay, how much time we have left? Can we quickly finish this? Already 3:30, huh? So shall we discuss this tomorrow? Ensemble based. I think there are only 1 or 2 slides left for this. Ensemble. Let me see. Yeah, well, I think better we discuss it tomorrow. Okay, ensemble based data assimilation. So, all right. So we're discussing that ensemble based. So we nowadays people, those who are having a very good computational facility, they use an ensemble based approach. Okay, where this tangent linear model provides a computationally efficient or the approximate way to calculate the model trajectory. I mean, this is the definition of tangent. What is tangent? Star. The tangent linear model, which calculate the model trajectory and from it the cost function. And similarly, the adjoint model is a very efficient tool to compute the gradient of the cost function. I mean, they are computationally involved. Gradient of the cost function, adjoint, that is the adjoint, and tangent linear model. So these are part of the 4D bar system, which are difficult to calculate easily. So people use ensemble-based approaches. Of course, that is also quite complex, but we shall discuss that tomorrow. All right. So we stop here. The time is up. Is that okay?
Yes,
Yes,
sir.
sir.
Okay. So so fine. I stopped sharing the presentation. Stop presenting, and also I stopped recording. Today also 4:30 class. I think today I have a meeting before, so we cannot have today's class. But a lot of things to discuss. Of course, now we shall be finishing the theory part soon. But I thought to take some classes for our practical additional classes, especially for the WRF part. Right. Anyway, today I stop. And today's file has gone to Haritasri. Okay. Stop
Yes, sir.
recording.